Hello everyone, welcome to my organic arrow pushing mechanism talk. Uh, Before we go to the detailed example today, I would like to remind you that arrow pushing always show the movement of electrons, always from a nucleophile to electrophile. Nucleophiles share electrons. They should have lone pairs or bonding electrons. And electrophiles, also known as Lewis acid, they always have empty orbital or partially empty orbital to accept electrons. So they always have a positive charge or partial positive charge. Today we will talk about the reactions of conjugated diene. It's a special compound. And first reaction is the hydrohalogenation. We can see the example. I use this 1,3-butadiene react with hydrogen bromide product. It's a mixture of 1,2 addition product and a 1,4 addition product. We call this 1,2 addition is because if we look at the number of the vinylic carbons, we have 4 vinylic carbons, 1, 2, 3, 4. And then if the hydrogen and the bromine add to the carbon 1, 2, that's 1,2 addition. If the hydrogen and the bromine add to the carbon 1, 4, that's 1,4 addition. Also, you can notice that double bond in the 1,4 addition product actually shifted to between carbon 2 and 3. And 1,2 addition product is always called a kinetic product because it forms faster than 1,4 addition product. But 1,4 addition product usually is called a thermodynamic product because it's more stable. If you look at this product, 1,4 addition give you di-substituted alkene. And this 1,2 addition is actually mono-substituted alkene. So the di-substituted alkene is more stable than the mono-substituted alkene. We will talk about the arrow push mechanism now, and we will see the detailed steps. First, the 1,3-butadiene will actually use the pi electrons attack this proton. Basically, it's a deprotonation of the hydrogen bromide, and that kick off the bromide as the anion and use the second step. Now, the first protonation actually will generate a intermediate. This is actually a secondary allylic carbocation. You have another choice. The carbocation should be here, could be here, but that's less stable, so we will not draw that. So this allylic carbocation actually have another resonance. So if you push the electron from this pi to here to form a double bond between carbon 2 and 3, then you will have this primary allylic carbocation actually. So you have 2 resonance here. So if you push the electron from this pi back to here, you can actually form this resonance again. So this is resonance. 2 different structures could give you 2 different products. Now, if the bromide here, from the first step, the bromide, if the bromide attack this carbocation, this can give you the 1,2 addition product. And if this bromide attack the other resonance, attack this carbon, and then you can form 1,4 addition product, shown here. So why the 1,2 addition product form faster is because the proximity principle, because after first step, this bromide should be closer to this carbon 2. So this addition will be faster than the addition to the other resonance because the distance is longer. This is more important if the temperature is very low. For example, negative 80 degrees Celsius, the bromide will move much slower than normal temperature. So it will most likely will attack this carbocation. So it will make the major product as 1,2 addition. A few portion of this bromide could move to the other side, but that will give you minor product. So, low temperature 1,2 addition product, the kinetic product should be the major product. At the higher temperature, like a room temp, this more stable product, 1,4 addition product, should be the major product. Okay, this is the first reaction we talk about today. Another reaction is halogenation of conjugated diene. And the example I shown here is the 1,3-butadiene react with the bromine molecule. And we also have 1,2 addition product and a 1,4 addition product. Let's look at the mechanism. First, the pi bond from the diene actually will attack this bromine, kick off the bromide as a living group, and then this bromine actually will use the lone pair attack back the carbon 2. So form a cyclic intermediate is called bromonium. And this intermediate can react with the bromide kicked off from the first step. If the bromide attack this intermediate, this carbon, and break this carbon-bromine bond, and this form the 1,2 addition product. If the bromide attack the other carbon, the carbon 4, and then this can push the pi electron and break the carbon-bromine bond, open the ring, and form another possible 1,4 addition product. So you can see the mechanism, it's pretty similar with the hydrohalogenation. The only difference is the intermediate is the cyclic bromonium. If you react with chlorine, then that will be chloronium. So it will be a similar mechanism. Okay, this is the second reaction. And then third example, the reaction of the conjugated is Diels-Alder reaction. Okay, so Diels-Alder reaction usually need a butadiene or conjugated diene and another dienophile. Dienophile need to provide at least one pair of pi electrons. So usually it's a double bond, it's alkene, or sometimes it's alkyne. If it's a half alkyne, that will just use one pair of pi electrons. So the product usually is a cyclic product. So if the dienophile is alkene, then the product will be cyclohexene. If the dienophile is an alkyne, then product should be 1,4 cyclohexadiene. Okay. Now let's look at the mechanism. This reaction, the mechanism is pretty simple, and the reaction is a concerted reaction. That means in one step they form the product. There's no intermediate. So the arrow position is actually just one step, 3 arrows. First, the pi electrons from here attack this dienophile, and then the pi electrons from the dienophile will attack the other end of this diene, and then push the pi electrons to carbon 2 and 3. So you form the cyclic product, and you can see I use the pink color highlight the newly formed bond, 2 sigma bond and 1 pi bond here. So that is the mechanism, arrow pushing mechanism of this Diels-Alder reaction. You can see it's pretty simple. The Diels-Alder reaction will keep the configuration of the dienophile because it's concerted reaction. So if you look at the example here, if you have a trans alkene, the 2 thionyl group are trans position, and then the product have also trans product. So they will remain the configuration. And if this diene is locked as a cyclic diene, for example, this is a cyclopentadiene, okay, and then this react with the dienophile will give you a bridged bicyclic product. So, and you can see this carbon, the bridge carbon here, was this carbon here. And so, and also if you have the substitution on the dienophile, the example here shows aldehyde. This CHO is aldehyde. Have 2 choices. It could be point down closer to the double bond, or point away from the double bond closer to this bridge carbon. And these two different products actually have two different names. The first one here is called the Indo product. This product is called the Exo product. Usually Indo product is major product and Exo product is minor product. Okay, so today we talk about the three examples of this conjugate diene and the mechanism. So if you have any questions, please let me know. Okay, good luck.